Okay, so we've talked a whole lot about energy now. We've introduced the equations. We've introduced an equation for conservation of energy. Let's practice using those equations to solve a problem or two. First off, here's just sort of a conceptual conservation of energy problem. Three balls are thrown off a cliff with the same speed, but in different directions. Which ball has the most kinetic energy just before it hits the ground? Is it ball A? Is it ball C? Or do they all have the same kinetic energy? So again, which ball has the most kinetic energy right before it hits the ground? Why don't you see what you think, and I'll see you on the other side. Well, let's look at this equation. This is our conservation of energy equation. So we're going to call this point up here at the top here, that's our initial point. And the point right down here, right before they hit the ground, is our final point. So let's go through and look at this. At the final position, they do have kinetic energy. At that final position, they're on the ground, so they have no potential energy. If there's no air resistance, there's no friction, so there's no change in thermal energy. Initially, they all were moving, so they do have some kinetic energy. Additionally, they were all at the top of the cliff, so they all had some initial potential energy. We'll talk more about that as we go along, but there's, that might be if we put a little propeller on the ball or something like that. Something else that could add some energy to the system with a push or a pull. A little doggy with a rope hooked to the ball. I don't know. That would be hard to contrive. But at any rate, there's nothing like that in this problem. So what do we have? We have that the final kinetic energy is equal to the initial kinetic plus the initial potential. So they are all thrown at the same speed. So they all have the same initial kinetic energy. They are all at the same top of the same cliff. So they all have the same initial potential energy. Therefore, they all have the same final kinetic energy. The correct answer is D, all have the same kinetic energy. Now, I think most folks like to pick A on this one because I'm throwing it down. But remember that these parabolas are symmetrical, right? So even if this ball is going, it's got some velocity here, well, once it gets over to this point here, that'll be going down, right? So A and C seem very similar. And what about B? It's going here. Well, you know what? It turns out the direction doesn't matter as far as the final kinetic energy. Lots of things will be different. Ball C will be in the air for the longest amount of time. Ball C will travel the farthest. They will have different impact angles, but what they won't have is different kinetic energies when they hit the ground. Again, conservation of energy. So that was kind of a conceptual problem. Let's talk about some steps for solving some more involved problems. First, we choose our system. It's the collection of interacting objects. Again, I don't think this is really going to be that as tricky as it seems when I just generally say choose a system. Once we get into the weeds of it, you'll find it's rarely difficult to choose the system. I could easily come up with problems where I define systems in different ways that are super tricky, but I won't, okay? So that typically is a fairly straightforward step. And much like we did with momentum, we draw a visual overview that includes a before and after picture. So an initial snapshot and a final snapshot. And then we apply this equation. And notice this is the same equation that I just had written up there. The difference is, in this version, I have separated out potential gravitational and spring potential. And so we could wrap these together. A lot of times there's not springs in problems. And so, we can wrap these together if we want to. If there's a few notes here, if there's no friction, then delta E thermal is always 0. If there's no friction, we're not creating thermal energy. And if your system is isolated, then work other equals 0. This is almost always the case. If there's a rope pulling on something or somebody pushing on something, there's some work being done on the system by some force that's hard to describe, hard to include as part of the system. That's when this will show up. But since we're wrapping friction up into the E thermal, work other will almost always be 0. We need to include it in the equation because that way it works for any situation not involving heat. But for most of the problems we solve in this class, work other will end up being 0. Let's do a couple of examples. Here we have Katie, and she slides down the water slide shown. If she starts at the point 9 meters above the bottom and she pushes off with an initial speed of 2 meters per second, how fast will she be going when she reaches the bottom of the slide? Neglect friction. Well, some of you might think that we would be able to solve this using kinematics, and kind of, sort of, yeah, maybe. The issue here is that since the slope is curved, she doesn't have constant acceleration. And all of our big 5 equations involve constant acceleration. We've never in this class dealt with motion problems, kinematic problems, or force problems where we had changing forces, changing acceleration, I should say. Okay, so that's why the techniques we've already had won't necessarily work in this situation, but energy will work great. So, they've already given us sort of an initial and a final overview, but we'll draw our own up here on our paper. Here is my person. That's my initial point. The initial is 2 meters per second. And she's up there at 9 meters. Down here we have y equals 0 at my final point. And we have v final equals, we don't know. That's what we're after. Okay, so there's my before and after visual overview. Now we need to apply the equation. The equation we're applying is this one. Let's go through and see if any of these terms are 0. Does she have kinetic energy finally? Yes, she does. Does she have any potential finally? No, she doesn't, right? We've defined this as y equals 0. And since we've defined that as y equals 0, that means u sub g equals 0 everywhere along this line, right? So u sub g equals 0 at the bottom of the hill. Okay, so that means there's no final potential energy. There's no friction, so we don't have any thermal energy. She does have some initial kinetic, and she does have some initial potential. She has initial kinetic because she's moving. She has initial potential because she's at the top of the hill. Be careful, often students think that an object will have either potential or kinetic. It can have both, one, the other, doesn't matter, right? They're kind of independent. Okay? So, are there any little doggies pulling on her? No little jet engines on the back of her. No, nothing like that. None of that. Okay, as is usually the case, that is 0. Now what we should do is we should plug in what I call the little equations for each of these terms. So kinetic final, that is 1/2 mv final squared equals 1/2 mv initial squared plus mgy initial. Notice I have an m in every term. And I do my algebra, and I get v final equals the square root of v initial squared plus 2 g y initial. And so now I can plug in my numbers, and I get, so there we have my numbers plugged in, and now I run my calculator, and I get, and so I ran my calculator, and I got 13.4 meters per second. Not too bad. Not too bad. Let's do another one. A sledder starting from rest slides down a 10-meter high hill. At the bottom of the hill is a rough patch of snow. The hill is frictionless, but the patch of snow at the bottom has a coefficient of kinetic friction of mu sub k equals 0.3. How far will the sled slide along the rough patch? Okay, so let's approach this from a conservation of energy perspective. If it was a straight hill, then we could do this using the physics that we've already learned, but it would be a pretty involved problem. And I think you'll be surprised to see how not so hard it is using conservation of energy. Okay, let's start by drawing our before and after picture. Okay. We don't know how far he went along this rough patch of snow. There's my initial point up here. And he starts from rest. So up here, v initial equals. That's my initial point. Well, I'm going to pick my final point over here. And my final point, well, he stopped there too, isn't he? Okay, so there we go. There is my visual overview. Here's my slider, I suppose. I've picked my initial and final points, and I've drawn my sketch. Now I should apply this equation. Okay, applying this equation, the first thing we should do is go through and see if anything is zero. Final kinetic energy, none of that, because he's not moving, right? No final potential energy, because he's where we called y equals 0, right? So u sub g equals 0 everywhere along that line, right? And so, again, we're calling the lowest point in our problem y equals 0. We're calling it potential energy equals 0. Gravitational potential energy equals 0. Is there friction? Yes, there is. So that one's not 0 this time. Initially, there is no kinetic energy. There is some potential energy because he's at the top of the hill. And no work other, as is usually the case. Oh my goodness. Okay, so we're actually doing pretty good here. E thermal is equal to delta x times the force of kinetic friction. And so now that equals m g y initial. So this delta x is what we're looking for, right? These are the same delta x, right? Because this is the frictionful, the part of the motion that has friction, right? Okay. F sub k, ooh. We might have to do just a really quick force problem to figure out what that is, right? So let's do that really quick. Free body diagram for the slitter when he's right here. We've got normal force, we've got the weight, and we've got F sub k. Well, from this, we can conclude that the normal force equals the weight, right? Because the net force in the y direction is 0. Okay, well, we know that F sub k equals mu sub k times the normal force. And so that allows us then to write delta x, F sub k, we're going to plug in mu sub k times the normal force, but the normal force is the weight. Oh my gosh, look at that. That is cute. Those cancel, and we have delta x equals y initial divided by mu sub k. If that isn't adorable, I don't know what is, and I have a 2-year-old. Okay. Y initial is 10 meters divided by mu sub k, which was 0.3. So we run our calculator, and we get 33.3 meters. Now let's check that out. Did we answer the question? Said how far will he slide? 30 meters, that's 100 feet. That's quite a ways. It must be a pretty nice sled. And 10-meter high hill, that's pretty high. And frictionless hills, you get going real fast down frictionless hills. So, I don't know. I think that's a pretty reasonable number. A lot of times when I do this, students get a little bit freaked out, and they say, well, what? How can you get away with doing this without figuring out how fast he's going here? You know, shouldn't this be our final point? Let's figure out how fast he's going here, and then we can figure out how far he went. Yeah, that would work too. But it would just be longer and more chances to make a mistake. This is the power of the conservation of energy. This is why scientists love this idea so much, is that we don't care what goes on in here, right? We don't care what shape the hill is. It could go up and down. I don't know. Like the exact details of the in-between initial and final, we don't really care so much about. We only care about the initial point and the final point. And I can pick the initial and final point wherever I want. This equation always holds true. I may not always be able to apply it. I may not have enough information to apply it at any 2 points. But this equation applies to any 2 points. Ever, right? And so we just want to apply it wherever it's the most efficient. And since we know everything about the energy here and we're asked about the energy here, well, then that's the way to go. We could find out the energy here. I mean, a different problem, I could say how fast is he going at the bottom of the hill? Well, we could do an energy problem to figure that out too. But I didn't ask that, so why include that? We don't need to. Initial here, final here, works great.